Okay, welcome back once again to the tutorial about the spectroscopy. We have been discussing about rotational spectroscopy. In the last video, we had discussed different types of molecule based on the different values of moments of inertia, Ia, Ib and Ic. Okay, today we are going to discuss more about rotational spectroscopy. Listen, we know that rotational energy levels are quantized, or only discrete energy levels are possible for rotation, and these energy levels can be obtained by the Schrodinger wave equation. We need not want to do more mathematics to solve the energy levels. We can directly use the result we have studied in Schrodinger wave equation. Okay, but the concept is, or the spectra discussion is different for different types of molecule. First, we are discussing diatomic molecule, a rigid diatomic molecule, that is during rotation bond length is fixed, no change in bond length. Okay, consider two hard spheres of mass m1 and m2 are fixed by a string, or we can consider as a bone having a length is equal to r. Length is equal to r. The center of mass point is here because this is a bigger sphere, smaller sphere, more close to the bigger sphere. This is center of mass C. So distance from the center of sphere, center of mass, here it is r1, it is r2. Okay, so rotation, the in plane and out of plane rotation, and we know that in this case linear molecule Ib is equal to Ic and Ia equal to 0. We have already studied. Okay, and during rotation the moments are balanced, so we can write the equation like this. We can write like this. There is m1 r1 is equal to m2 r2. Okay, therefore the moment of inertia I is equal to m1 r1 square plus m2 r2 square. Okay, and for or this we can write, that is m1 r1 into r1 plus m2 r2 into r2. And for this m1 r1 we can write m2 r2 because m1 r1 is equal to m2 r2. So we get equation like this, that is m2 r2 into r1 plus, for this m2 r2 we can write m1 r1. Therefore there is m1 r1 r2. Therefore r1 r2 is common here, so we can take it outside, that is I is equal to that is r1 r2 into m1 plus m2. Okay. And now another step is, here from this equation we can write m1 r1 is equal to m2 r2, and that is equal to m2 into, for r2 we know that the total length r0 is equal to r1 plus r2, that is r0 is equal to r1 plus r2. Therefore r1 is equal to r0 minus r2 and r2 is equal to r0 minus r1. Substituting this for r2 we can write m2 into r0 minus r1. Okay, and that is equal to m2 r0 minus m2 r1. Taking this m2 r1 this side, here m1 r1 is here, so we can write m1 r1 plus m2 r2 is equal to m2 into, we can write here m2 into r0. Okay, from this we can write, what I am writing, minus m2 r1 taken this side. Therefore, we get m1 r1 plus m2 r1 is equal to m2 into r0. And here r1 is common. Therefore, we can write r1 into m1 plus m2 is equal to m2 into r0. Therefore, r1 is equal to m2 divided by m1 plus m2 into r0. Similarly, we can write from the same step, by the same step we can write r2 is equal to m1 divided by m1 plus m2 into r0. Therefore, moment of inertia I is equal to, for r1 and r2 we can substitute these two equations. So we will get m2 divided by m1 plus m2 into r0, okay, and m1 divided by m1 plus m2 r0, okay, and one m1 plus 2 m2 is already here, that is m1 plus m2, and that is cancelled. Therefore, we get m1 into m2 divided by m1 plus m2 into r0. That is sorry, r0 square, 1 r0 here, r0 square. That is, we can write here I is equal to mu r0 square, mu r square or mu r0 square, and this mu, that is equal to m1 m2 divided by m1 plus m2 is called reduced mass. This already you already know this equation. This moment of inertia I is equal to mu r square or mu r0 square, where mu is called a reduced mass, that is equal to mu is equal to m1 m2 divided by m1 plus m2. Okay, next step is, okay, from quantum mechanics we know that the energy of a rigid diatomic rotator we have already studied in quantum mechanics by using Schrodinger wave equation, solving Schrodinger wave equation. We get the equation, that is Ej is equal to h square divided by 8 pi squared I into j plus 1. This equation we have already studied. Energy of a rigid diatomic rotator is equal to h square divided by 8 pi squared I j into j plus 1, where I is the moment of inertia, and h we know Planck's constant, and j is called a rotational quantum number. That is, energy levels are quantized by the quantum number j, and j can have values from 0, 1, 2, 3, etc. up to infinity. As many numbers are possible. And this is the equation for the energy of a rigid diatomic rotator. And this energy is in joule. And if we write the energy in the form of wave number, we can write, that is energy in wave number epsilon j, or another way we are also called as fj or epsilon j, is equal to Ej divided by hc, to convert energy in wave number, because in spectroscopy energy of radiation mainly used, or energy is used mainly in wave numbers, that is easy to handle. Therefore, to get the energy in wave number divided by hc, so we get we get h square divided by, we can write here, h square divided by 8 pi squared IC into h, that one h is cancelled, into j plus 1. That is, we get h divided by 8 pi squared IC, that is one h is cancelled, h divided by 8 pi squared IC into j plus 1. Okay, and this term, that is h divided by 8 pi squared IC, is denoted as B. Okay, so we write EJ is equal to B into J plus 1. Okay, where B is called a rotational constant. Rotational constant, like rotational constant. That is B is equal to h divided by 8 pi squared IC. H divided by 8 pi squared IC. Okay, and if you calculate energy, there is energy of rotational levels in terms of wave number, epsilon j is equal to B into J plus 1. You can write B into J plus 1. Okay, so when J is equal to 0, that is the lowest rotational level, we get Ej is equal to, or epsilon j is equal to 0. That is energy of the ground state. Ground rotation level is 0. That is, in ground level there is no rotation. Molecule isn't rotating. Okay, and when J is equal to 1, epsilon j is equal to, here 1 into 1 plus 1, that is we get 2b. And when J is equal to 2, epsilon j is equal to 2 into 2 plus 1, that is equal to 6b. Okay, and when J is equal to 3, epsilon j is equal to 3 into 3 plus 1, that is 3 into 4, that is equal to 3 into 3 plus 1, 3 into 4, that is 12, that is we get 12b. And when J is equal to 4, epsilon j is equal to 4 into 4 plus 1, 5, that is equal to 20b. Okay, that is rotation levels are like this. This is 0, first level is 0, second level is 2b, third level is 6b. This is first rotation quantum number. J is equal to 0 here, J is equal to 1 here, J is equal to 2 here. When J is equal to 3, it is equal to 12b. This is 12b, that is J is equal to 3, and another term is 20b. J is equal to 4, and so on. As many levels are possible. That is, with increasing rotational quantum number, the spacing between energy levels are increasing. Okay, first is 0, second 2b, 6b, 12b, 20b, and next is 5 into 6, that is 30b. Next level is 30b. Okay, like that. This is the rotational energies, rotational levels. Okay. And if we calculate the energy for transition from one level to the next level, that is from 0 to 1. So we can calculate it as E j is equal to 1 to E j equal to 0. And that is equal to, j is equal to 1 is 2b. So it is 2b minus 0 is equal to 2b. So first line is observed at an energy of 2b. And second line, that is from first level to second level. And before that, you have to understand one thing. The selection for rule for rotational transition. Selection rule is selection rule. First, one selection rule is molecule should have a permanent dipole moment. Permanent dipole moment. Okay, that is a one selection rule for rotational transition. For rotation to be active, rotational transition possible, molecule should have a permanent dipole moment. Okay, that is only heteronuclear diatomic molecules like HCl, CO, etc. can show rotational spectrum. Homonuclear diatomic molecules like O2, N2, etc. cannot show rotational spectrum because they have no permanent dipole moment. And second selection rule, that is obtained from quantum mechanics. We are not going to derive the selection rule. It is already obtained from the Schrodinger wave equation. That is, only transition from delta J is equal to plus or minus 1 is possible. Okay, that is transition only from the one level to the next higher level. Okay, that is from 1 to 2 or 2 to 3 or 0 to 1, like that. No transition with the delta J is equal to plus or minus 2, plus or minus 3, etc. is possible in the case of rigid diatomic rotate, that is obtained from the Schrodinger wave equation. So selection rule is delta J is equal to plus or minus 1. That is a rotational selection rule for transition. That is, only transition from a level to the next higher level is possible. So from J is equal to 0 to 1, the line is at 2B. And from J is equal to 1 to 2. So energy difference is J is equal to 2 minus J is equal to 1. And that is equal to J is equal to 2. What is the energy? 6B. So 6B minus J is equal to 1, it is 2B. 6B minus 2B, that is again it is equal to 4B. Okay, and next level is from, or generally we can write J is equal to, only possible transition is from next higher level. So we can write like this: J plus 1th level minus Ej. Okay, we can derive a general equation for the energy of the transition. That is, from energy of the J plus 1th level minus energy of the Jth level. And that is equal to, for J plus 1th level we can write B into J plus 1 into J plus 1 plus 1. Okay, minus B J into J plus 1. And that is equal to B into J plus 1th level, that is J plus 1 into J plus 1 plus 2, that is J plus 1 into J plus 2, minus B J into J plus 1. B we can take an outside. J plus 1 into J plus 2, that is equal to J square plus 3J plus 2 minus J square minus J. Okay, J square is cancelled. 3J minus J is equal to 2J. 2J plus 2. Okay, so we get B into 2J plus 2. This we can write 2B into J plus 1. Okay, so that is the equation to calculate energy of the transition from any for any transition from the next higher level, 2B into J plus 1. So from 0 to 1, we get J is equal to, we are putting J is equal to 1. Sorry, J is equal to 0. Okay, therefore we get it is equal to 2B. For 1 to 2, we are putting J is equal to 1. Here J is the lowest level. Okay, for this equation, J is the lowest level. So we are putting J is equal to 1. So 2B into 1 plus 1, that is equal to 4B. And transition from J equal to 2 to 3. So equation is J equal to 3 minus J is equal to 2. Putting this equation 2B into J plus 1, where J is the lowest level. Lowest level is 2. So 2 plus 1, 3. 3 into 2, 6 is equal to 6B. And the next level, next transition, that is from J is equal to 3 to 4. So energy is J is equal to 4 minus J equal to 3. Or I am meaning epsilon, J is equal to 3. So here put J is equal to 3 here. So 2B into 3 plus 1. 3 plus 1 is 4. 4 into 2, 8B. So it is 8B. And so next level will be, okay, it is 10B. We can say 2B, 4B, 6B, 8B, 10B. Okay, so the lines will be like this. You can see here. In rotational spectra, the lines, okay, first line is at 2B. Second line is at 4B. Third line is at 6B. Fourth line at 8B. Fifth line at 10B, and so on. Okay, that means difference between the lines, it is 2b, this is also equal to 2b, this is also equal to 2b. That means rotational levels or rotational transitions are equally spaced. Rotational lines in the spectrum, we get different rotational levels for all the possible transition from 0 to 1, 1 to 2, 2 to 3, like that. And all these lines are equally spaced at a space of 2b. That is, spacing between the lines in rotation spectroscopy is constant. For in the case of rigid diatomic rotator approximation, if we approximate rotator is rigid diatomic, then the rotational levels are equally spaced. The spacing between the lines is equal to 2b. Okay, clear? Then, okay, see this picture. The energy levels, when J is equal to 0, when J is equal to 0, energy is 0. When J is equal to 1, energy is 2b. When J is equal to 2, 6b, 3, 12b, 4, it is 20b, and so on. When 7 is equal to 56b, like that. And transition from 0 to 1, it is equal to 2b. From 1 to 2, it is 4b. 2 to 3, it is 6b. 3 to 4, it is 8b. Okay, from 20 minus 12, that is 8b. And here it is 4 to 5. 4 to 5, it is actually, it is 30b. So 30 minus 20, it is 10b. Okay, it is actually 42. Therefore, 42 minus 30 is equal to 12b. Okay, next is 56 is equal to 14b. 56 minus 42 is equal to 16b. That is, lines are like this at 2b, 4b, 6b, 8b, 10b, 10b, 12b. That is, lines are equally spaced. In rotational spectra, the lines are equally spaced. Okay, clear? Oh, and I'm stopping here. We have studied that rotational levels, rotational energy E is equal to h square divided by 8 pi squared I into j plus 1. When it is converted into wave numbers, that is epsilon j, we get h divided by 8 pi squared IC into j plus 1. And this term is called rotational constant B. So we can write epsilon j is equal to B into j plus 1. By substituting the values of j, 0 to 1 through etc., we get the rotational lines. 0, for j is equal to 0, it is 0, 1, 2b, 6b, 12b, 20b, 30b, 42, 56, like that. And the selection rule is, first selection rule is, molecule should have a permanent dipole moment. Second selection rule is, the only transition from next higher level, that is delta G plus or minus 1, is possible. So by calculating, we get an equation for transition, that is E j plus 1 to Ej. Okay, from j level to the j plus 1 level. That is, equation will be E j plus 1 minus Ej is equal to 2b into j plus 1. So when j is equal to 0, we get 2b. When j is equal to 1, 1 plus 1, 2 into 2, 4b. Okay, next j is equal to 3, 3 plus 1, 4 into 2, 6b. Next 4, 4 plus 1, 5 into 2, 10b. Next 6 plus 1, 7, 12b, like that. Okay, so the main point here is rotational lines. In rotation spectroscopy, in the case of a rigid diatomic rotator, rotational lines are equally spaced. Okay, I'm stopping here. We will discuss more about the rotation spectroscopy in the next video. Okay, thank you.